Let's see. So this presentation is one of several this morning that talks about critical minerals. And because I'm the first speaker, I'm going to try to give a little perspective and background on the general topic. So the US government's identified approximately 50 critical minerals or elements that are in great demand for clean energy and other modern technologies, including defense, and for which global supply chains are vulnerable to disruption. A lot of these minerals or elements are coming from China and Africa and other countries where there's really not any guarantee that they'll be available for the US economy or for defense and other purposes. So there's been a high priority by the US government put on this topic prior to the current administration, but especially now they're putting an emphasis on it. So more than half of these elements are included in the geochemical models that I've created, and they're shown in their respective positions on the periodic table. And the models are called the Freak and AMD treat plus REYs. So for those of you that have maybe used the AMD treat code, we've incorporated a water quality modeling capability into that. That's primarily a cost analysis model, but we put this water quality model in there that allows us to evaluate the potential effects from different treatment strategies on the removal of contaminants of concern. It also applies to these other minerals that could have value if recovered from the water. So these water quality models will be explained in more detail later. That's going to be the focus of this presentation. Let's see what else I got here. I have notes and it doesn't show me anymore, so I'll just leave it at that. Well, actually, the rare earth elements is the focus. So the rare earth elements are shown at the bottom of the periodic table, the lanthanide group rare earth elements. There's 15 elements on the lower tier, plus scandium and yttrium that are often combined with the lanthanide rare earth elements. And from left to right, the atomic radius decreases and the atomic weight increases. So in general, they tend to behave similarly and co-occur, but there are differences resulting from their different ionic radius and weights. And these things are actually, to some extent, indicated by the modeling. It's interesting the way these things separate from water in the environment, and that could be useful if we're trying to separate them for economic purposes, because ideally you're able to separate one element from another and concentrate it. And that's the goal of the recovery, is to concentrate these things from the water. So a long time ago, 1999, we sampled water chemistry from mine discharges across the state as a USGS project. And we also sampled again in 2011 sites that were actually permitted. The 2011 study was supported in part because the EPA was questioning the DEP's and other states' approach to regulating mine discharges, because basically it's iron, aluminum, manganese, maybe sulfate, and pH that are regulated, and they're saying there's a lot of other contaminants of concern that are in mine water that would be, any normal industry would be required to meet effluent limits. And so we sampled discharges from around the state, and both the untreated and then the treated water at these regulated facilities to see, well, if they're meeting their effluent standards for iron, manganese, and aluminum, what's the fate of these other metals? And it turns out, as a part of both these efforts, we got a lot of data on rare earth elements in the mine water, both pre and post treatment. So we could say something about what their fate is and how that relates to the changes in pH and iron and aluminum and these other metals. So compared to river and seawater, the dissolved rare earth elements concentrations are highly elevated in coal mine drainage, like orders of magnitude, several orders of magnitude. And the total rare earth element concentrations range upwards to about 2,000 micrograms per liter in the samples we collected. And they tend to be highest in the bituminous coal mine discharges, which in general have lower volume flows and in general also have higher concentrations of other constituents like sulfate than the anthracite discharges in the east. However, the anthracite discharges generally have, although they had low rare earth element concentrations relative to the bituminous, they have much higher flow rates. And consequently, they can have very high loads of the rare earth elements in the discharge. And the big red dot that's shown, actually the eastern middle field sites, I'll see if I can use the pointer, right in this vicinity, are ones that had both low pH and high loads of rare earth elements. And the biggest dot is the Jet-O tunnel, which is the largest volume discharge in the anthracite region. It also happens to have low pH. Now, the rare earth element, the pH of abandoned mine drainage across Pennsylvania has a bimodal frequency distribution. About half the discharges have pHs in the 3s-ish, and the other half is around the 6s. And interestingly, the rare earth elements are elevated in the low pH discharges, but there's a distinctive break in slope at about pH 5. So how do we account for that change in chemistry? Is there something going on that can explain why the rare earth elements are less abundant instead of just like this linear trend? And that's what, again, I'll get into with the modeling. So one way this change in slope might be explained is due to adsorption, and another is possibly due to the precipitation of a phase such as a phosphate mineral. As it turns out, most of the rare earth elements it's believed that most of them in the rock, in their native form, in these sedimentary rocks associated with coal, are present as phosphate minerals. And it would make sense, perhaps, that that type of a phase could limit their concentrations in solution. Now, anyone that knows geochemistry, there are a lot of minerals that just don't behave with respect to equilibrium, like silicate minerals, are predicted to be supersaturated, but that you won't see them precipitating from solution. So anyway, I just wanted to point this pattern out. It's, how do we understand what mechanisms are limiting the concentrations, both from the perspective of will they be present and maybe of interest in a recoverable context, or is there a mechanism by which we can concentrate these elements and recover them from the low pH drainage? So for example, if you increase the pH of a low pH discharge, would we precipitate a phosphate phase as a mechanism for recovery? And then the other option is potentially adsorption. So in general, the rare earth elements accumulate with the iron, manganese, and aluminum that precipitate as hydrous metal oxides in AMD. So all of you have seen this orange or white or black gunk in the, that tends to accumulate. And as reported by Hedden and others, this is Ben Hedden, and I think Bob might even be a co-author, the rare earth element concentrations generally occur in solids with mixed compositions. So these solids that have iron, manganese, and aluminum, the aluminum's blue, the black is manganese, and the orange is iron, those tend to have the highest concentrations of rare earth elements. But it turns out that for the most part, those mixed composition solids are formed from low pH mine water. And then these that are predominantly iron, we get these circumneutral waters that have a lot of ferrous iron. At high pH, they don't have rare earth elements. So you're going to precipitate this iron from those waters, and you just don't get rare earth elements with the solids because they're not in the water to start with. So adsorption is an interesting phenomenon where these solids have charges on their surfaces that change as a function of pH. And so at low pH, they have a positive charge. Think of protons, low pH. They give the surface a positive charge, and when they're positively charged, they attract anions, which are negatively charged, things like phosphate, arsenate, and sulfate, which is the dominant ion in mine water. As it turns out, the idea that they attract sulfate become really intriguing because sulfate, once it's absorbed, gives the surface a more negative charge than it would have, more negative charge than it would have otherwise. So as we go to high pH, then the surfaces become negatively charged, and that's when they attract cations, which is what rare earth elements are. Rare earth elements are like a +3 cation, like aluminum or ferric iron. So in the models presented herein, the manganese oxides are simulated to exist as these manganese +3 hydroxides, or the manganese hydroxides with a +2. And the iron oxide is the ferric hydroxide, or these hydroxysulfate compounds like schwertmanite. And then the aluminum oxide is the aluminum hydroxide, and then another hydroxysulfate called basaluminite. These have different solubilities, so that's why they have to be kind of considered as separate phases when we're trying to account for the removal from a solution of aluminum or iron, but we treat them as a group, as a sorbent. So HAO would be the aluminum oxides, and it could be a mixed composition sorbent. So there's new empirical data that were collected, in part because of the modeling that helped guide this work by Travis Tasker and some other colleagues and we're able to demonstrate the importance of sulfate on affecting the adsorption of the rare earth elements by these iron oxides and aluminum oxides. It turns out that and we were able to model it by saying, first we adsorb sulfate, and then that gives a negative charge to the surface. At lower it basically effectively gives it a attraction to the rare earth elements at a lower pH than where it would be attracted without sulfate. And then I created these models initially without the rare earth elements, and then we just added the adsorption and precipitation of the rare earth elements. But so basically, as I mentioned in the beginning, the models were developed to simulate water quality changes during passive and active treatment. And the results of these models can be used with AMD treat cost analysis model to evaluate alternative designs and costs. And there are three different models that I'm describing here that sort of complement one another. The first set of models are these caustic titration models where you're basically increasing pH, and you increase the pH with potentially different caustic agents, like maybe we use sodium hydroxide, maybe we use calcium oxide, which is lime, or maybe we use calcium carbonate, which would be something that's present in a limestone bed. And those so the caustic titration models are equilibrium models, instantaneous oxidation of iron, for example, or manganese, which in reality, it takes time. It doesn't happen instantaneously. And the only difference between the two caustic titration models is whether the input data are in milligrams and micrograms or in moles. It just helps to have the units in the options for different input units. And then the second set is this treat train model, which is similar to what was incorporated into AMD treat. It's a sequential model that incorporates kinetics. And the kinetics apply, I'll explain that later. But, and then there's graphical and tabular output that indicates the changes in the pH and the corresponding changes in concentrations of solutes, including things like total dissolved solids and specific conductance, which may be of concern, for discharge water quality. We might want to consider a different treatment strategy that's going to have a lower dissolved solids in the effluent than another one as an option. So this gives us some flexibility to consider different treatment strategies. And with respect to the rare earth elements and other elements, we might select a treatment strategy that allows us to recover those and concentrate those as, let's just say, a byproduct of our primary goal, which is to get clean water. Now, this user interface, it's really busy looking, but the point of this is we can input data. You don't have to know how to do coding in geochemical models like Freak. Anyone in this room could use this model. You put your numbers in, and you have some options to change variables. So I have some blue boxes around different things. So just the left side, these would be our major ions. And we can mix two solutions. We can mix solution A and solution B in different proportions before we do any kind of reactions. And then this next one over are trace elements. So this part here are a lot of these contaminants of concern, perhaps. Some of those are actually critical minerals. And then the lower part are the rare earth elements. And in this particular case, we're looking at molar concentration units. We have sorbents, which is interesting, the way I've set this up. I don't know that anyone else has ever done this. This is the fresh precipitate. This would be the stuff that's coming out of solution from the input starting concentrations of the metals in solution. So we can precipitate these when you reach equilibrium. And then this would be the pre-existing sorbent. So when Mike, I think it was Mike, that was talking about, or Tom Clark yesterday was talking about recirculated solids. If we have solids that have already accumulated on like a limestone bed, or we're recirculating them, those are effective sorbents. And they exist in much higher concentrations perhaps than would have been present in the starting solution as a dissolved metal. So we can actually add the fresh precipitate to this pre-existing solid in this model. And we can give them different characteristics if we choose. We can make the fresh precipitate maybe a higher surface area than the pre-existing one. Then we can say at what point we allow these minerals to precipitate. Some of the minerals might form sorbent phases. Some would actually be able to sequester the rare earth elements directly, like the phosphates, or possibly carbonates or oxalates. So at any rate, there's a lot of opportunity here to investigate the importance of different variables and different mechanisms for sequestration and recovery. And we can use different caustic titrants. And so if you add calcium, that might affect something else versus adding sodium. And we get graphs on the screen that show up. By the way, I've been doing this for years. It's not like I did this yesterday. It's like it gradually just continues to get more and more complicated. But this is a good illustration of what the importance of the sort of interactions in the system. This is a simulation of what was on that user interface, showing the results of this simulation where we don't have sulfate in the water to start with. So we're just saying, what happens if you have all these metals and no sulfate? And what's interesting here to point out, we have light rare earth elements represented by lanthanum. It's primarily absorbed by manganese oxide. So at about pH 6-ish, 7, we could, you might think you could recover lanthanum on manganese oxides if they're present. And in contrast, europium, which is like a middle rare earth element, tends to be more associated with the iron oxides and less so with the aluminum, whereas the heavy rare earth element lutetium is associated primarily with the aluminum oxide. So this all starts out in the same water, right? But at the given pH, they could be associated with different phases that might be present in a mixed sludge or a mixed system. Now, when we add sulfate to this system, and it's a fairly high concentration, 500 milligrams per liter, it's actually a typical number for mine water, especially in the bituminous area, we see a diminished importance of manganese absorbing lanthanum and an increased importance of iron. With europium, it's now almost entirely associated with iron, and same with lutetium. So this is because of that sulfate absorption on the iron oxides that enhances the iron as its as an effective agent for recovering these rare earth elements. Now it's the same caustic titration model, but now the units are in micrograms and milligrams, and this is where I actually titrated a water in the field. So this was like one of the waters that had the highest concentrations of metals that we sampled. We went back out to the field and titrated and said, what happens when you add sodium hydroxide and get to certain pH intervals? And we adjusted the pH, I think 6, 7.5, 9, 10, and then just at each of those pH intervals, we sampled it and said, what's remaining in the water? And this is, again, I'm not going to explain the interface except one thing. I did vary the surface area on this fresh precipitate because it helped me explain the data a little bit better. And it just shows how we can adjust these variables to improve our simulations. So the first upper 6 graphs, we're able to simulate the changes in the sodium and calcium and aluminum and manganese reasonably well. And then the rare earth elements, lanthanum, gadolinium, and lutetium in this case, it's showing that they're being removed at somewhat lower pH perhaps than what would have been expected or observed. And then all I did was decrease the surface area. And these numbers that I decreased are actually consistent with what's been measured. There's a wide range of these numbers. These are sort of mid-values. The upper ones, which are the default values, are actually what's reported in the literature, sort of the upper end. And now we're getting a little better simulation. So I've used then these same surface areas in subsequent models. So you'll see that in the next models. So now I'm going to use this treat train mix 2 model, which is the one that incorporates kinetics of iron oxidation. Well, first of all, I'll just read the list. So this is to simulate sequential changes in effluent chemistry through successive treatment steps. And the model actually allows us to simulate 11 successive steps. So the water from step 1 is passed after it reacts, and whatever remains in that water goes to step 2. And whatever remains after step 2 goes to step 3. That's this idea of the sequential model. And at each step, we can have changes happening that are kinetically limited. In other words, that means how much time it's available for the reaction to occur. We have things like atmospheric exchange. We talked about decarbonization yesterday, so that would be CO2 outgassing. But when you get CO2 going out, you have oxygen going in. And this is basically due to atmospheric equilibration. And that's not instantaneous, but we can make it happen faster by aerating the water and by aggressively aerating the water. And so this is a kinetic process, just to sort of get that point across. You know, shake the soda can, like I was saying yesterday. Now, iron and manganese oxidation are pH-dependent processes that's well known. I just used numbers from the literature for kinetic models, and they work. The other thing is there's iron bacteria that can catalyze iron oxidation. And there's acidophilic and neutrophilic bacteria. How much time, am I doing okay?
Oh, no, you're good. The other presenter's here.
Okay. Anyway, and then we get organic carbon oxidation, limestone dissolution, and adsorption and precipitation reactions. So now I'm going to show you a simulation where I had some data that I could actually try to explain. This is the Silver Creek wetland in southern anthracite field. It's one of the largest wetland systems in Pennsylvania that I'm aware of. And the water starts out at step 0, comes out of the ground. It's an upwelling discharge. It's basically anoxic. It's a pH near 6. It's less than 6, but it's moderately net alkaline. But there's a lot of ferrous iron in the water, negligible aluminum, and actually not a great deal of rare earth elements, but there are rare earth elements in it. And I had some data that I could simulate. Now, the first 2 ponds are massive. They account for about 4/5 of the residence time, which is the time needed for reactions to occur. And you can see all this iron oxidation occurring in the first pond, and then less of it occurring in the next pond, and then 2 wetland cells. What's really important are between these steps are these level spreaders. These are like shallow, wide, passive aeration devices. Very thin film, allows a good exchange between the water and the atmosphere. And we can get almost as effective aeration from these passive devices as can be achieved with like these maelstrom oxidizers, these things that require a continuous input of energy. So we get about a pH unit increase, almost going from like a pH 6 to 7, or at least a half a unit, just by going across these level spreaders. And once we have a higher pH, now the iron oxidation occurs much faster. It's a pH-dependent process. So that's why you start seeing all this orange in that pond. And you have some suspended particles, so we're getting a little bit of maybe the equivalent of recirculated solids, right? So you're not all the water, you know, like the iron that started in the water, it's not all moving. Even once it precipitates, some of that precipitate stays behind and stays in suspension. So that's all factored in here. This is the interface, and then I put blue boxes around a couple variables that I tried adjusting to see what seemed to explain our observations. And so one of these things was iron oxidizing bacteria. In some systems, they're really important. 5 minutes, we're good. And then, you know, what about precipitation of rare earth elements? I can turn that on or off. And then, do we have existing sorbent? This would be the equivalent of the, suspended particles in these ponds. So those are the variables that I have showing in these results. We'll just say the first one that had the iron oxidizing bacteria active is this orange curve, and it overpredicts the amount of iron removed. The other models do not have that catalysis effect built in, and they all seem to do the same thing as far as iron removal. The only other thing that varies here is whether their sorbent existing or not. The final model is basically where I don't have iron oxidizing bacteria. I do have existing sorbent, and we allow rare earth elements to precipitate. That would be here. So like without the precipitate, we don't get so it's a combination of absorption and precipitation occurring. That's the bottom line. We'd have to do a little more further analysis to say exactly, what's present. The student I worked with at the time actually did the measurements of the rare earth elements in the solids, but it's difficult when you're dealing with a trace mineral, even identifying it. And this is just some other elements. And, we do pretty good with, I think, what is that, arsenic? Yeah, arsenic, copper, lead, they're all well predicted. Even zinc's pretty good, but cobalt and nickel, not good. And I think those could be better explained as a co-precipitation with manganese, and that's not in this model. So when the manganese oxidizes, does cobalt go with it? And that's likely the mechanism that could explain the removal of cobalt, but it's just not built into this model. Now, the last thing, and I've got like probably 2 minutes left now, is just to apply the model in a scenario where we may be able to recover rare earth elements from water. In this case, it's leachate from a coal refuse disposal facility. The interesting thing is the rare earth elements are not concentrated in the coal. They're associated primarily with the shales and the underclays with the coal. That's what's removed and stockpiled at these refuse disposal facilities. And they're operated much like a landfill. They have a liner and a leachate collection system, and then they have to treat that leachate. And if we could recover the other part of this is those coal refuse disposal facilities, they're going to have to be operated and maintained for years and years, long after any coal mining is continued and they're continuing to receive coal for cleaning. So if we could recover rare earth elements, that might help offset the treatment costs. I'm not telling you that we're going to be able to make a bunch of money off these things. So the current strategy, you can see in the background, there's this pile of stuff with grass growing on it. That's actually the mound of coal refuse, and it's being, again, imagine it like a landfill. And then the leachate comes out, they're adding lime to it, and then this green rust is precipitated. It's ferrous hydroxide. And then at this particular facility, they pump the sludge and the water right back down into the mine pool. They're not recovering anything of value. So the first scenario is just simulating the current treatment strategy where everything comes out as a sludge. The rare earth elements come out as a sludge with the iron, the manganese, the aluminum, and calcium, any excess lime, it all comes out in the sludge. And you could recover rare earth elements from it, but you'd have to basically redissolve it with acid and go from there, which is what some people have been doing. Then the next thing is let's consider trying to remove the iron first and keep the pH low enough that it won't absorb the rare earth elements, so that we're basically trying to concentrate the rare earth elements so that they could be recovered in a subsequent step. Iron's the dominant metal here and the dominant contaminant, and we can remove most of the iron just by using peroxide. And then the effluent would still have the rare earth elements in it, and then we pass that to the next step. And that ultimately we could recover the rare earth elements by absorbing them to manganese oxides, or possibly by precipitating them as phosphates. So that's what I'm simulating here. And so this is the results. This is the last results slide, and then the next one just conclusions. So the orange is, the status quo, and we're not recovering anything. It's all getting pushed back down into the mine pool, but we're getting neutral water. And there's actually, because we're adding lime, you're getting a bunch of calcium gypsum being precipitated, which may or may not be a good thing. It's not necessarily what we would want in our sludge if we're trying to concentrate rare earth elements. But with this red dash, that's where we're using peroxide, getting the iron out. So the iron all precipitates pretty rapidly, and it is a very fast thing. It happens like you drop peroxide in this water, it turns orange instantly. And then the aluminum doesn't change so much, nor does the manganese. It's not until we increase the pH sufficiently that the aluminum will precipitate, and even higher until we get the manganese. But in the meantime, a lot of the rare earth elements stay in solution. Some of them come out with the aluminum, but the majority comes out with the manganese. So that's scenario one for a strategy to recover rare earth elements. And then scenario two is where let's take the water after we've added the peroxide and let's put in some phosphate. Let's see if we can precipitate these phosphate phases, and that's what the blue curves are. I'll just get to the point. We're able to get almost all these rare earth elements, and this is simulated, it's not demonstrated, but we could get these rare earth elements to concentrate as a phosphate phase. And now we're actually working on the demonstration. Is this feasible? So I'm working with Travis Tasker again at St. Francis, and this is sort of like a phase 2 project where we're looking at, how we can use the model to guide empirical work, guide the, pilot scale if we can get to that point of the recovery. So here are the conclusions. The Freak and AMD treat plus RE-wise cools incorporate equilibrium aqueous and surface speciation plus kinetics models. These are common processes in treatment facilities, both active and passive. The field and laboratory studies that demonstrate attenuation and corresponding aqueous-solid interactions can be actually accurately simulated. Now, sometimes we need to know more about what variables to adjust. And that's important when we're actually trying to, go forward. Potential treatment steps may be indicated that concentrate the rare earth elements with adsorbing solids. Now, the idea with the adsorbing solids, it might be easier to recover the rare earth elements. If you increase pH, they adsorb. You might be able to decrease pH and get them to desorb without dissolving the iron or without dissolving the aluminum. And then last, the AMD treat software can be used to evaluate the costs for any sort of a treatment strategy. And the benefit of that is we can do cost benefits analysis. So now, you get an effluent, what's its result? How much did it cost to get to that end result? A different strategy is going to have a different cost. You may have the same end result. So you choose a strategy that's going to be the least costly and achieve the benefits that are desired. And then last, this is just for those of you that are interested, there are some documents, the software is available, and there's some documentation of it. That's it. Thank you.